Hey, welcome to the course. I just sent out an announcement that some students did not register online. So I think let me just double check with Marika. Yeah. Okay, let's wait for her reply to clarify exactly what she means. So I updated the course homepage. Mainly with additional readings, optional readings. So for the introduction and overview part, there's a 2020 Autonomous Vehicle Technology Report by a Revolver, which is a technology research company. It's pretty comprehensive. I took some of the pictures from this report. It covers pretty much every aspect of the autonomous driving, sensing, thinking and learning, acting, and so on. So it's a very good overview and non-technical overview of the field. So I highly recommend it. And also I put up links to a few massive online courses. One is this self-driving car specialization at Coursera by Steve Waslander from University of Toronto. So it's a sequence of courses. So you can take the free option. Okay, what happened here? It used to be free. Okay, if you click on courses and then click to individual courses, I think you can register for free. At least I did it last year. I'm not sure if it's not free anymore. You can try and tell me. So did anyone try to see if you can access the courses for free? Let me see, where's my chat? Okay, I didn't see any, it works, okay, yeah. So this course is mainly on the classic techniques. So including state estimation with a Kalman filter, localization, visual perception, they discussed convolutional neural networks, motion planning, it's classic planning algorithms. So there's another course on Udacity taught by Sebastian Throne, who was used to be a professor at Stanford. He founded Udacity later, and he's a pioneer in the self-driving car area. So this course is very hands-on. So I took one of the labs, this PID control lab from the course with a few links from a few videos. So another sequence of 4 lectures, 5 lectures from University of Bonn in Germany gives a very good overview of the various aspects, perception, planning, and control for self-driving cars. He has a few other courses on more of mobile robotics, which are also very, very interesting. So this course is new from ETH in Switzerland. Self-driving cars with Duckytown. Duckytown is this simulated environment where you have little ducky cars driving around in a simulated artificial town. They have Olympics. This AI driving Olympics every year. You can enter online. So this course has just started, so there's not much material yet. They have only a few chapters online. This is based on ROS, Robotic Operating System, and Gazebo Simulator that works with ROS. It's also focused on classic robotics techniques. Not much machine learning. So, and then functional safety, a few videos, just a simple introduction. And this is a collection of latest machine learning and deep learning courses. I will also provide the introduction to machine learning, just to bring everyone to the same page. For the convolutional neural networks, I put up a few links from UC Berkeley and from a blog, as well as a full course on deep learning for computer vision from University of Michigan. A blog on recurrent neural networks. So the next part is adversarial robustness. So I will mainly discuss this tutorial from a conference in 2018. So it talks about what is adversarial robustness. That is, you add a few pixels onto this cute picture of a pig and turns into fools the classifier into a wrong decision, into a gaboon. So it comes with the Jupyter notebooks you can run either locally or on Google Colab. So I will discuss, it also comes with a video online, 2-hour lecture video. So I will discuss this tutorial in class, and then you can basically adapt their code. Their code is written in PyTorch. Adapt their code to apply to the traffic sign pictures. So it's not a very complex assignment. And for the control part, I put up a few, there's a class from the Udacity course that talks about control, PID control, and also a few YouTube videos. For reinforcement learning, this is the Bible, the golden textbook for reinforcement learning. You can download the PDF. And it's very readable. So this book is not so mathy. So you can, it's an easy read. I highly recommend it. This course taught by a professor from the UK, I forgot which university, a professor from University of Durham. So it follows the textbook by Sarton and Bartle closely, reinforcement learning course. Basically chapter by chapter. So it's an introductory level course. And then these other two courses, one is from UC Berkeley, one is from DeepMind. These are more advanced. So you may have some difficulties if you watch it before learning the textbook. So if you want to study ahead, I highly recommend you to go through the course by Chris Wilcock from University of Durham. That's an intro level course. But also, obviously, I will start from the intro level. For the labs, I found a course by Jeff Heaton from University of Washington University in St. Louis. This course is very hands-on. So they have modules. First module is on Python preliminaries. Second is on Python for machine learning, and TensorFlow, Keras, and also so on. So every module has a YouTube video. As well as the Jupyter Notebook. You can directly open in Colab and run the all the lecture material. So this is a script that stops a Google Colab from disconnecting. So if you have a free account at Google Colab, it times out after some time. So I think it's free online. Disconnect after a while. I think it's a few hours or something. And then if you use their script, it kind of tricks Colab into a not disconnect. But I wouldn't expect the assignments to take too much time. So maybe you wouldn't need it. And then I pull up the lab 3 first. I'm still working on the other labs. Lab 3 is on PID control. So essentially you control a small dot, a car, to track this particular shape. And if the car, you can imagine if the car speed is too high, you may lose control, right? So you can tune the PID controller gains to maintain control of the car. So we give you Python programs for the controller, and you modify it to add automatic tuning of the controller gains, and also try to only use P control with only the proportional term, or PI control with proportional integral, and or full PID control. And also, if you increase the car speed too much, you may lose control. And then you can decrease the time step size to maintain control. So this lab is based on this particular program from Audacity. So you can watch the short lecture and the sample code they provide. So all the assignments are still ongoing, still working on them. So I would expect the first one to come out after I finish lecture 4 on CNNs. So it should be 1 or 2 weeks from now. And also I added a link for anonymous feedback. It's a Google form. You can type in anything anytime during the term. Okay, so let's continue. So last class, we discussed the history and overall picture of autonomous driving. So it all started, the modern age of autonomous driving started from the DARPA Grand Challenges, the 3 grand challenges. But there were earlier attempts, which I did not discuss. Back in 60s and 70s, there were some early attempts. But the modern era started from the DARPA Grand Challenges. And we discussed 5 levels of automation. Today's vehicles, especially, for example, Tesla, is level 2. And there's a large gap between level 2 and level 3. Certain vehicles can claim to be level 3 or higher in a limited ODD, operational design domains. For example, in a limited area of the city with high definition maps and so on. But in general, for unlimited driving, there's with unlimited ODD is the higher levels of automation is not available. So and then we discussed 2 different paths. So Tesla is starting from mass deployment, level 2, and gradually trying to improve their technology to reach higher levels of automation, whereas Waymo and Autonomy are working with a fleet of test vehicles, not consumer vehicles, only for testing, and starting from level 4, and gradually pushing for mass deployment. And we discussed some accidents, high-profile accidents by Tesla and Uber vehicles. So all of the accidents we discussed are really mainly due to perception errors. So it highlights the importance of perception for autonomous driving. So, but also planning and control are also challenging. So now we discuss the overall AD processing pipeline. So we covered this part. Mainly, you can think of the 3 stages, sensing, planning, and acting. So sensing the environment with multiple sensors. The most common ones are Lidar, camera, radar. And then you perform motion planning, including high-level mission planning and low-level local planning. And finally, you perform control to track the plan given by the planner. And for the processing pipeline, the current industry practice is to use the machine learning, deep learning for perception only. And there are some attempts at applying machine learning to part of the motion planning or end-to-end, mapping from pixels to commands. So that's more in the research stage, mainly done by a few startup companies and industry research labs. So now we'll discuss sensors and perception in this class. So here's a picture of a downtown large city. So you can see the variety of static and moving objects that an AV needs to detect and recognize. So the static objects are the parked car, street signs, traffic lights, lane markings, road markings for pedestrians, moving objects, moving cars. So it's a very complex thing. So perception is very challenging. This is a video from 2015 recorded by Google's autonomous vehicle. Wait, let me turn on the computer audio. Disable, hide, share computer sound. Oh, I hope you can hear it. Let me, okay, I think it works.
Woman in an electric wheelchair with a broom, chasing it in the road. So since then, we've seen people play Frogger with our car. Please don't. And then, you know, honestly, Austin kind of takes the cake. So here, we're at an intersection. That's 1, 2, and wait for it. That's 3 cars going the wrong way down the road, all at once. That was fantastic. We had this. Some dude comes out of nowhere, decides to roll on our hood, and then run away. And then this is great. So, you know, people are interested in our car and want to see how it reacts. So this guy was apparently so excited that he came running out without his clothes on. So really, I just want to say thank you, Austin, for keeping it weird.
I think we missed the beginning. So
He's a duck and a woman in an electric wheelchair with a broom chasing it in the road.
yeah, so anything can happen on the road, even a woman in a wheelchair chasing a duck.
Is a duck.
So the typical AV sensor configuration looks like this. The camera, video camera, is the most versatile sensor. Can detect a traffic light, read road signs, keep track of the position of other vehicles, and so on. The Lidar, light detection and ranging device, uses a laser to identify objects. And the radar on the front monitor the position of other vehicles nearby. And GPS, global positioning system, are combined with other sensors to provide localization information. You have a backward-facing radar, and you have ultrasound, mainly for parking. So I collected some information on the sensors of some research AVs, a number of cameras, a number of LiDARs and radars. So 8, 16 cameras, LiDARs could be 1 to 10 LiDARs, and radars could be 1, 2, 4, 8. So noticeable is that Tesla does not use LiDAR. It's one of the few AD companies that do not use LiDAR. So Elon Musk said famously in 2017 that once you solve cameras for vision, autonomy is solved. If you don't solve vision, it's not solved. You can absolutely be superhuman with just cameras. In my view, LiDAR is a crutch that will drive companies to a local maximum that they will find very hard to get out of. Perhaps I'm wrong and I will look like a fool, but I'm quite sure that I'm not. He is right that indeed humans can drive cars with vision only. Why not machines? But the problem is that there are so many corner cases that computer vision just still have difficulties, even with today's deep learning. You saw a few accidents where the Tesla car mistakes white trucks as the sky. So it happened multiple times. So these are corner cases that are very hard to handle. So if you had a LiDAR, it would be much easier to handle, especially with sensor fusion. The key issue with LiDAR is its cost, especially for mass deployment vehicles such as Tesla. Adding tens of thousands of dollars to the car's cost may not be feasible. So sensors can be divided into passive sensors and active sensors. So passive sensors include cameras, detect existing energy like light or radiation reflecting from objects in the environment. Whereas active sensors, also called range sensors, send their own signal and sense its reflection, including LiDAR, radar, and ultrasound. So they use different spectrum in the light, different frequency bands in the spectrum. Cameras are in the visible light spectrum. LiDAR and the thermal camera that's infrared, not very common for autonomous driving. Radar is here. So that's the wavelengths of the different sensing devices. So cameras are cheap, versatile, and you can have stereo vision with two cameras, just like human eyes. With two eyes, each eye capturing a slightly different image, you can get stereo vision. So the con is that it's easily affected by illumination conditions and needs additional light at night. So the key parameters are resolution. For example, a 1080p HD camera provides 1920 times 1080 pixel resolution, or 2.1 megapixels. Field of view, so that's the extent of the observable world that's seen at any given moment. Given the same resolution, a wider field of view results in large image distortion. So a solution is to place multiple cameras pointing in different directions and use computer vision methods, image processing techniques to stitch them together, maybe into a bird's eye view, or maybe into a clear view with no distortion. So dynamic range, so it refers to the maximum difference between the darkest and lightest pixel intensities in an image, measured in dB. So autonomous vehicle needs HDR, high dynamic range cameras, with at least 100 dB. So our range sensors rely on time of flight to measure distance or range, which is the key element for localization and environment modeling. LiDAR uses electromagnetic waves, radar uses radio waves, ultrasonic sensors use sound waves. So the traveled distance of a wave is given by d equals v, distance equals speed of wave propagation times the total round trip time divided by 2, because it's a round trip. So you need to divide by 2 to get the distance from the sensor, the range sensor, to an object reflecting the wave back to you. So the propagation speeds vary a lot. Sound is very slow, 0.3 meters per millisecond. Electromagnetic wave, including light, travels at 0.3 meters per nanosecond, 1 million times faster than sound. So for example, to travel 3 meters, it takes 10 milliseconds for ultrasonic sensor and 10 nanoseconds for LiDAR. So therefore, to measure time of flight with electromagnetic signals is not an easy task. So LiDARs are expensive and delicate. So the quality of range sensors mainly depends on the inaccuracies in the time of flight measurements for laser range sensors, because the time is so short, and opening angle of transmitted beam for ultrasonic, and interaction with the target depending on the reflecting surface, and variation of propagation speed for sound, and also speed of vehicles and target. That is the relative speed between these two. So let's first look at LiDAR. LiDAR sends out millions of light pulses per second in a well-designed pattern to generate point clouds that describe the 3D geometry of the surrounding environment. So here's a picture of a LiDAR. You have the optics device sending out laser beams reflecting off an object back to the device, which receives the reflected laser beam and detected by the photo detector and processed by the signal processor. The computing unit takes the time difference from emitting the light beam and getting the reflected light beam back and computes the distance to the point, to the object. So a very simple principle. Here I show a picture of a building because LiDAR was originally widely used for geography, for surveying of large objects or large areas. For example, using a drone with a LiDAR to map a certain area. And then its use in autonomous vehicles is more recent. So here's the point cloud collected by LiDAR. You can see rough shapes of objects, pedestrians, cars, buildings, and so on. So the colors are added later by the processing algorithm. So all you get back from the LiDAR are a collection of points. You don't know anything about these points unless you process them with perhaps machine learning, perhaps more classic computer image processing methods. So, and you can see that it's not very detailed. So you cannot see exactly, you cannot see color, cannot see texture, cannot see any language. All you get is a collection of points in space. So that's why LiDAR is a very good complement to cameras. They can be used together, whereas the LiDAR can detect obstacles very well, and cameras can tell you the traffic sign, the traffic lights, and other more detailed information. So the pro is that it's independent of lighting conditions, and you get precise distance measurements for 3D perception. You can get 3D perception with 2 cameras, but still the distance is not as precise as LiDAR. The con is that it's expensive and resolution is medium. Depending on the LiDAR's specification. So the key parameters are laser beam count, rotation speed, if you have a rotating LiDAR, field of view, and range distance. You can have tens to hundreds of meters. So the most well-known LiDAR company is Velodyne. Here's Uber's car with a Velodyne Lidar on top. So it's a high-end Velodyne with the model name HDR64E with 64 laser emitters. It rotates at a high speed, up to 15 Hertz. That is 15 rotations per second. So the field of view is 360 degrees horizontally because it rotates, and 26.8 degrees vertically. And angular resolution is 0.09 for horizontal and 0.4 for vertical. So that's similar to image resolution. How detailed is the point cloud? What's the minimum distance between 2 points? So it delivers 1.3 million data points per second. That is the points in the point cloud, 1.3 million points. It's very expensive. It costs $40,000 to $80,000. There are cheaper versions. So many companies are working on LiDAR today. And it's not just used for self-driving cars. It's used for consumer products also. With many applications in space, topology, wind, transportation, and so on. So the Velodyne's LiDAR is a mechanical LiDAR. There are newer technologies such as MEMS and other new technologies coming up. So iPad Pro has a built-in LiDAR. You can see that you can capture the objects around in the indoor environment. If you turn off the lights, you can see the point cloud. So this is after processing. So after the algorithms processing, you can see more information than points. So the main application for the iPad is for augmented reality. That is, you can place virtual objects in a physical environment. This needs depth information. So radar uses millimeter wave radar. It provides both position and relative speed information. So the information it gives you is very sparse. Essentially, it tells you there's an object 50 meters from you moving towards you at some certain speed. So it's not like a LiDAR, which is a high bandwidth sensor. So the radar has a low resolution. The key parameters are sensing distance, field of view, and position, and velocity accuracy. So there are two types. One is a short range to medium range with wide field of view, and long range with a narrow field of view. So radar was originally a military technology. You know that large lidars scanning the large radars scanning the sky for enemy airplanes, right? So it's used in consumer products. It's relatively recent. Ultrasound is short range sensing, mainly used for parking assistance. The pro is that it's not affected by lighting conditions, rain or fog. The con is that it's short range. The key parameters are sensing range and field of view. So here you can see it's a very small opening in the front with the ultrasound. Typically you have ultrasound all around the car. So a comparison of sensing ranges. So LiDAR is 3D environment mapping and object detection with 360 field of view. And cameras, you can place cameras. Here we show 4 cameras, front, back, and 2 sides. So the front camera has a longer range, maybe with a higher resolution. And long-range LiDAR in the front for object detection through rain, fog, dust. And you may have short and medium range radar, the dark circles, for object detection, including side and rear collision avoidance. And finally, you have the very short range, a few meters range, ultrasound for parking. So each sensor has its strengths and weaknesses. Therefore, sensor fusion is crucial for robust perception. So you can compare the 3 sensors in terms of sensing range. So mixed means that you can have either short or medium or long range depending on the model. Functioning in bad weather. So camera is not very good in bad weather. Functioning in poor lighting. So camera is not good. Object detection. So camera is mixed. LiDAR is good. Radar is mixed. Object classification. So camera is good. Because visual information is very detailed. You can classify traffic signs, traffic lights, and a lot of more detailed information, whereas LiDAR can only give you a rough classification of objects, not the detailed information. So lane tracking, camera is good. Yeah, because lanes are just lines drawn on the road. So from the LiDAR or radar perspective, they cannot really see it. So for localization, GNSS and GPS are used. So a global navigation satellite system provides localization services for outdoor applications, including GPS from the United States, Galileo from Europe, Beidou from China, GLONASS from Russia. So traditional GPS provides a few meters accuracy affected by cloud covers and tall buildings. So you may find that GPS location is not very accurate if you walk in a large city with many tall buildings. So there's a real-time kinematic GPS, RTK GPS, which can provide centimeter level accuracy by calculating and transmitting differential correction data via radio to allow the roving GPS system, the vehicle, to correct its position. So a regular GPS has just the vehicle, the device, communicating with the collection of satellites to localize with triangulation. Whereas for RTK GPS, it needs assistance from a ground base station on the right. So therefore, from the base station, which also receives GNSS data from the satellites, the device gets RTK corrections, which can correct the direct GNSS data received by the device and get a very high accuracy. So IMU, inertial measurement unit system, measures the acceleration, including linear and angular, and orientation, including yaw, pitch, and roll. So here are the 3 angles of orientation. So for ground vehicles on the 2D plane, only yaw is relevant. That is the turning left or right. For aerial vehicles in 3D space, all 3 are relevant. So they're often combined with GNSS as GPS to form a so-called integrated navigation system, INS, using sensor fusion to achieve higher estimation accuracy. So for example, if you go into a long tunnel with a temporarily disrupted GPS signal, you may use your IMU to estimate your position based on the speed times time, the basic Newton's law. And once you get the GPS, you may perform a Kalman filter-based sensor fusion to get a more accurate estimate. So wheel odometer measures the distance traveled by counting the number of wheel rotations and multiplying it with the tire circumference. The accuracy is determined by slippery road surface, which causes the tire to move without rotation, and severely worn tires, which affects the tire circumference. So the perception tasks include detection, that is to detect the existence of an object in the environment, and classification to identify what the object is. For example, traffic sign, traffic light, pedestrian, and tracking to track a moving object across time, maybe with temporary occlusions. Segmentation, including semantic segmentation to classify each pixel to its semantic category, a road, car, sky, or instance segmentation, which to classify each pixel to an object instance. For example, car 1, car 2. So here's a Mobileye's autonomous car. Mobileye is an Intel subsidiary company in Israel. So they have a pretty leading technology in terms of camera and the associated AI algorithms for autonomous driving. So you can see the green is the drivable road, and the red are the pedestrians. And here you can see the traffic lights, other vehicles, and so on. So this video demonstrates detection, classification, and tracking, and also segmentation of the road surface. So there's no need to segment the other tall buildings. The important part is the road and the lane. So AV sensors generate big data. Cameras and Lidars generate the most amount of data. They are high bandwidth sensors. The other sensors are relatively low bandwidth. For example, radar is a few tens to 100 kilobytes per second. Sonar is also GPS 50 kilobytes per second. But cameras and Lidars, especially if you have high resolution sensors, they can generate lots of data. So they must be processed in real time by the perception algorithms. So high definition maps. So here's an example of a high definition map. It has information on the lanes, the traffic lights, the wall, barrier, bike lane, stop line, crosswalk, and so on. So it's different from navigation maps. For example, Google Maps, designed for human eyes. HD maps are designed for processing by computers. It's highly accurate, centimeter level accuracy with 3D representation of the road network, including cross-section layout, locations of traffic lights and signs, semantic information on certain road segments, for example, speed limits. The benefits are reduced region of interest for detection of traffic elements. So, for example, if you are driving in a very complex urban scene, so looking back at this picture here, so now the most important thing now is perhaps to detect this traffic light. Looks like it's turning red. So if you don't have HD maps, then you need to scan the picture with a deep learning algorithm to find a match for a traffic light. So which may be time consuming and may be inaccurate. But if you have a high definition map, it will tell you that at this particular location, this particular traffic light is at this height and this coordinate. So the algorithm can directly look in that spot to look for the traffic light. So that's what I mean by help reduce the range of interest, region of interest for detection of traffic elements. It helps with AV localization based on known object positions. So you know where all the objects are, so you can localize yourself pretty well. Helps with recognition of lane center line. So here's a few pictures on what the high definition map looks like. The traffic light position, the traffic speed limit position for each segment of the road, and left turns, straight lanes. So are high definition maps necessary? For example, humans don't need HD maps to drive. So HD map limits the area of operation. That is, limits the ODD. Whereas mapless systems allow universal operation anywhere. So use of HD maps reduces the computational burden on onboard sensing. The more that has already been mapped out, the easier it is for the onboard system to focus on the moving parts. Whereas a mapless system must figure out everything on the fly from scratch with no prior knowledge of the environment. So it's generally agreed that L4, 5 levels of automation cannot work without HD maps, at least for now. L2, L3 levels may work without them. For example, Tesla does not use HD maps. Whereas the L4 level vehicles, say from Waymo, they rely on HD maps. Okay, so I think we'll take a few minutes break. Oh, okay. There. Do I see chat? Okay. Can you share the link to the course 7 days trial free access? Okay. 7 days trial. You mean the Coursera, or what do you mean? Mazen. So you can write in the chat later. GitHub. Okay. Sure, but the GitHub is always free. Okay. Yeah. So this page, yeah, this page is always there. So yeah. Okay, so let's, I think it's time for a break. Let's take, okay. Set alarm. Oh, Coursera course is not free. Oh, okay, Martin says Coursera is not free. Let me see. So, I mean, if you go into the, if you go into the specialization and click on enroll, so it's not free. But if you click on courses and directly click into the courses, at least for me, it's free. I don't know, maybe because I registered very early. I'm not sure if it still works if you register now. It's free if you select audit. Yeah, that's what I figured. If you click here, there's no audit option. But if you click on the courses, in each individual course, I think you can just register. Yeah. If you can't, let me know. So let me set a alarm for, okay, let me see how this works. A timer for 10 minutes. Okay, see you later. Okay, so I hope everyone is back. I just got a reply from Marika Falk, who is responsible for the course registration. So I asked, do you mean LADOC registration? And she says it's LADOC. So some students did not register in LADOC. So in that case, you can send email to me or to Marika. Let me put her email. Send email to Marika Falk. Okay, so let's discuss hardware platforms. So here's a picture of the typical automotive electrical electronic architecture, EE architecture. So you have Ethernet as the high bandwidth backbone network. The dominating standard is Ethernet time-sensitive networking, TSN. The regular Ethernet may also be used for non-real-time applications, such as diagnostics. But Ethernet TSN is a standard for hard real-time systems with strict timing guarantees for messages on the bus. FlexRay for safety critical X-by-wire systems, where X stands for brake, steer, and drive. So, but it's gradually being replaced by Ethernet. Most media-oriented systems transport is mainly used for multimedia transmission. And it also gradually being replaced by Ethernet. CAN, controller area network, it's for low bandwidth network and interfacing with sensors and actuators. And LIN, local interconnect network, is for body electronics, such as doors, light, rearview mirrors connections. So the trend for in-vehicle networking is to have Ethernet as the backbone network with CAN and LIN networks extending to sensors and actuators. So automotive EE architecture has been evolving from many 80 to 100 distributed and networked ECUs to a few high-performance ECUs with massive computing power and large number of ECUs, smaller ECUs for interfacing with sensors and actuators. So ECU is the automotive terminology for computer, electronic control unit. So on the left is the classic ECU architecture. The green is the performance and safety ECUs, and the black is the smaller ECUs for interfacing with the sensors and actuators. And on the right, you can see that the performance, high performance control is getting more and more centralized. Here we have 4 high performance ECUs, and 60 or so smaller sensor actuator ECUs. So the centralization trend helps to simplify system architecture, reducing network load, and improve system reliability. So here's a trunk of the experimental AV from Ford in 2017. Obviously, the first question to come is that maybe this car is not ready for consumers because no consumer will buy this car. There's no place to put your groceries. So after all, it's an experimental vehicle, but for mass deployment for production, you need higher efficiency, smaller computers. So AD hardware considerations are power consumption. So power consumption for AD may be 100 times that of a vehicle with regular ADAS, advanced driver assistance. So this drains battery and implies increased fuel consumption or reduce the range for EVs, electric vehicles. So EV drivers often turn off air conditioning in the summer due to range anxiety. That is, they are afraid that the car will break down on the road. I mean, will they turn off AD function and drive manually for the same reason? So Waymo and Ford now focus on hybrid vehicles, while Uber uses a fleet of full gasoline SUVs for their autonomous vehicles. So you would think that a new technology, autonomous driving is such a new technology, obviously it should be combined with electric vehicles. But you know, some companies are turning to more conventional fuel source just for the reason of high power consumption of the computing elements. Cooling capacity, you may rely on traditional fan cooling or liquid cooling. Form factor must be compact and unobtrusive. Shouldn't occupy an entire trunk. Cost is important for mass deployment. So cost of electronics in the experimental AV often exceeds the cost of the original vehicle. So most notably the Lidar. It may cost, you know, the entire car may be worth less than the Lidar. But things are improving. There are cheaper versions of Lidar coming out. The most compute-intensive workload is deep learning. Deep learning has the training and inference stages. So for deployment in the vehicle, it's mainly inference, but it may also perform training tasks for online learning and distributed federated learning, perhaps. So many vendors provide SoC, system on chip, products that integrate CPU cores with specialized computing elements for deep learning. The most common is GPU. Nvidia is the only serious player in GPU for deep learning. So other GPU vendors such as AMD, ARM, Intel, they focus more on computer graphics instead of general purpose computing called GPGPU. So you all know the Nvidia GPUs for training deep learning models, but they also provide products for embedded systems such as cars. So FPGA, Field Programmable Gate Array, is essentially programmable hardware with vendors such as Xilinx and Intel's Altera. They are also very active in the automotive space. Application-specific integrated circuit, ASIC. So it's there are an explosion of specialized ASICs for deep learning in recent years, with hundreds of companies and products ranging from high performance to embedded. And digital signal processors are mainly used for image pre-processing. That is, a raw pixels come in, you first perform some conventional image processing, computer vision algorithms with DSP, and then hand them over, maybe resizing, maybe some preliminary processing, and then hand over the pixels to deep learning. So DSP is typically used for pre-processing. It's not powerful enough for deep learning. So Texas Instruments is the leader in DSP. So a CPU versus GPU. GPU has more simpler control logic than CPU, hence has more computational elements, so-called ALUs, arithmetic logic units, the green parts. Whereas a CPU has large control and cache and the DRAM, and these are needed for a complex auto-ordered CPU to work properly, whereas GPU has very little control logic. It's ideally suited for processing highly parallel workloads, especially matrix multiply, which is a core operation in deep learning. So here's an analogy of CPU versus GPU. When you plow a field with 4 strong oxen, a multi-core CPU, or 1024 chickens, that is a GPU with many smaller engines. Each engine is very weak, but overall, the parallel computing power is very high. Similar arguments for FPGAs and ASICs. So Nvidia, they provide the Drive family of products. It's a trademark. So ranging from low-end Parker to latest high-end Orin with 200 tops tera operations per second. So you can see the product comparisons. So besides the CPU and GPU cores, they also include NVIDIA Deep Learning Accelerator, NVDRA, which is an ASIC for deep learning inference. So it can achieve higher performance with a lower power consumption than GPUs. So FPGA is a reprogrammable hardware consisting of an array of configurable logic blocks and interconnections which can be configured at design time or runtime. So CRBs, memory, and DSP blocks, and I/O on the sides. So you can download the bit stream either offline at design time or even at runtime to reconfigure the FPGA to perform a different task. So FPGA versus GPU. So for inference tasks, FPGA has advantages because a GPU performs computation in batches for efficient exploitation of the SIMD, single instruction multiple data computational model. So this is very suited for training tasks with well-known algorithms such as stochastic gradient descent with mini batches. That is, you collect a mini batch, maybe here 4 inputs, could be 4 images, and you process them in batch and produce results in batch. So, so this is very good for throughput, but may not be very good for individual tasks latency. So for example, here, input 4 has a very small latency, whereas input 1 has a pretty large latency. But especially if you have large batch size, it leads to high throughput, but also high and non-deterministic latency for each data item. Whereas if you use smaller batch sizes, it leads to low computational efficiency because GPU has so many parallel elements. If you have small batch sizes, the computing engines are not used efficiently. Whereas FPGA can perform batchless inference. That is, each one is processed individually. Input 1 comes early, it finishes early. Input 4 comes late, it finishes late. Therefore, it has low and deterministic latency for any batch size. So FPGAs can be integrated into sensors such as camera, Lidar, and radar, so-called smart sensors, or serve as central compute engine in domain controller or AD computer. So right now, Xilinx FPGAs have 90% market share in Lidars that is to implement the Lidar processing algorithm FPGA. Intel is pushing hard into the market with acquisition of Altera in 2015. So this shows the Zinc product from Xilinx either for processing camera, radar, or Lidar data, or as a central controller, central computing engine in the autonomous vehicle.
May I ask a question?
Oh, yes.
So FPGA, as you said, so here, normally we have to design the FPGA program before and we have to synthesize it, right? And then only you can deploy it to the FPGA. So how we can deploy a machine learning model with pre-existing, pre-trained model there?
Let me see if there's any more information in the link. So this is Xilinx product page. So they have AD processing modules, data aggregation, and computing. Okay, so FPGAs are very flexible. That is, you can reconfigure the FPGA by downloading a bitstream at design time or runtime. So if you have a trained network, a trained deep neural network, you can configure the NM parameters into the bitstream and configure it at design time, for example. That's the most common scenario. And maybe after a few months, you have a newer version, a deeper network, a better network. You can just reconfigure it by downloading another bitstream. So it's very convenient. That's the advantage of FPGA versus ASIC.
Yeah, sure. I mean, we can reprogram it anytime. That's, yeah. Okay, thank you.
Yes. So I think FPGAs can be used for training, but it's for training, its benefit is less compared to GPUs because GPUs can perform the batch operation very efficiently. But FPGAs are more suitable for inference.
Yeah, thank you.
Yeah, even for ASICs, the application-specific integrated circuits, they have a certain level of reconfigurability. For example, you may store the DNN parameters in RAM, in memory, and the ASIC just implements a generic framework for executing the neural network. And for example, if you change from AlexNet to ResNet, for example, you may download the new network architecture and parameters into the memory, but the ASIC itself does not have to change.
But if you keep it on the RAM, I mean, that means it's transient memory, right? So if you switch it off, probably that's gonna be gone. So probably it's gonna be wrong instead, right?
Yeah, probably
okay.
flash, the permanent storage.
Yeah.
Yeah.
Is TPU from Google? I think it's also ASIC, right?
Yeah. TPU is ASIC.
Yeah.
Yeah, so even for ASICs, it can process different deep neural networks with no problem. But maybe the compute, the hardware, the fixed part is less flexible than FPGAs. So if you have drastically different learning algorithms, maybe ASICs cannot handle it very well, but FPGAs have infinite reconfigurability.
Yeah, I was just thinking in terms of Python, because when I did some work with FPGA, I had to program in VHDL. So it's completely different than Python. So I don't know how people convert this Python program to VHDL or Verilog that can be deployed to FPGA.
I think it's manual. I don't think there's any tools. Yeah, you gotta convert it manually.
Okay.
Yeah.
Yeah.
So ASICs for deep learning are often called neural processing units or AI accelerators. Thanks to a dedicated circuit design, may achieve up to 10 times in computation efficiency and power consumption compared to a CPU, a GPU, and less dramatic but still significant improvement compared to FPGA. The drawback is loss of programmability and flexibility. So industry, almost every chip vendor provides some kind of AI accelerator, too many to list. Academia, so AI accelerator is a dominating topic in top conferences in computer architecture. So Mobileye is a key player in the computer vision for AD perception. So they provide ASICs for different purposes, from the early products for driver assistance to latest products for highly autonomous driving. So here's the overall architecture. CPU, 8 CPUs, and computer vision processors. These are the ASICs, and other security and other modules. So Tesla full self-driving chip, FSD, is designed by Tesla and introduced in 2019. Integrates 3 quad-core Cortex A72 clusters for a total of 12 CPUs and a GPU operating at 1 gigahertz, 2 neural processing units, NPUs, operating at 2 gigahertz, and other accelerators. So NPU is ASIC. So these two. So there's a trend for OEMs, that is original equipment manufacturers, that's Tesla, Ford, GM. They used to rely on suppliers. For example, Tesla used to rely on Mobileye for their perception system. but they decided to develop their own products later. They hired many computer vision researchers to develop their own deep learning algorithms and also their own hardware. So there are also products from automotive OEMs and suppliers. They don't design chips, they offer integration solutions based on products from chip vendors, such as Nvidia. So Delphi Audi has the ZFAS, which is a German abbreviation based on Tesla Tegra K1 and Mobileye's IQ3. So it's not common to see Nvidia and Mobileye's products integrated together. These are pretty much fierce competitors. ZF is a company. They provide a Pro AI based on Nvidia Drive Pt2. Bosch has a system based on Nvidia Drive AJX Xavier. And Continental, Visteon, NXP, Renesas, each one has a product. But different from Tesla. Tesla is developing their own chips, but these companies are just doing integration. So for a software platform, so AUTOSAR, Automotive Open System Architecture, is a global development partnership of automotive interstate parties founded in 2003. It pursues the objective to create and establish an open and standardized software architecture for automotive ECUs. Pretty much all the major OEMs and suppliers are members of AUTOSAR. Here's the AUTOSAR Classic platform. This existed way before autonomous driving for any kind of ECU, large or small. So it has a real-time operating system and all the standardized interfaces for communication, for device drivers, and so on. The adaptive platform is a newer standard for developing future automotive ECUs running on high-performance multi-core processors. So whereas a classic AUTOSAR is for resource-constrained, safety-critical ECUs, whereas the adaptive AUTOSAR is designed for high-performance ECUs and allows dynamic linking of services and clients during ECU runtime, which facilitates over-the-air updates. So here's the AUTOSAR adaptive. It has operating system with different services, execution management, time management, and so on. So the key is that the SWC software components runs on the AUTOSAR runtime and can be dynamically switched, linked, and unlinked. So it provides very flexible service-oriented computing architecture. So AUTOSAR Classic and AUTOSAR Adaptive are not mutually exclusive. They are intended to coexist in a vehicle. So AUTOSAR CP is used for safety-critical ECUs for low-level control and interfacing with actuators, whereas AUTOSAR AP, labeled A, is used for high-performance AD computer, autonomous driving computer. And also you may have non-AUTOSAR systems. For example, this computer for in-vehicle infotainment and communication with the outside could be based on Android or Linux. So here's the exemplary interactions of AP and CP. So, so the adaptive platform performs the environment, driver state, and vehicle state perception, and maneuver and the planning. And then when it generates a trajectory, a plan, it hands over to the safety critical ECUs running AutoSAR CP that carries out the control functions to follow the trajectory, to do trajectory control. And also the preliminary processing of the camera, Lidar, radar data may be going through the classic platform and then processed by the adaptive platform. So AutoSAR is an initiative from the automotive industry. It started very early in 2003. So many of the newer technology companies in the space do not use AutoSAR. For example, Waymo. I think Tesla does not use it either. So it's more of the traditional automotive OEMs, such as GM, Ford, Volkswagen. So they use AutoSAR a lot. Robotic operating system, ROS, is called an operating system, but it's not. It's just a middleware. It's a set of software libraries and tools for building robotic applications. Many companies use ROS to develop AVs. It uses a publish subscribe paradigm for inter-node communication. ROS version 1 has a master node that provides naming and registration services to the rest of the nodes. ROS 2 removed the master node and uses DDS, data distribution service middleware, for decentralized communication. So ROS relies on Linux as the underlying OS. So it's not possible to pass high level of safety certification. For example, SOD. So subsystems with different safety critical levels integrated together form a mixed criticality system. So here's the figure shows the AutoSAR ROS 1 versus ROS 2. So ROS 2 took away the master in ROS 1 and relies on DDS. Underlying platform mainly is Linux or Windows or Mac OS. So if you want to learn ROS, you may look at that link on DuckyTown. Yeah, this course is based on ROS. Now it only has a few chapters online. But I won't discuss ROS in this course. So APEX is a so-called safe and certified software framework for autonomous mobility systems. Aims to be certified as a safety element out of context. That is the ISO 26262 standard has the SCOC section. So it's built built on top of ROS 2, but added a few modifications such as hard real-time static memory allocation with no new or malloc, which can cause problems at runtime, and a few other features, and based on real-time Linux or QNX for the operating system. Another company's product is EB Corbus. EB is an automotive supplier in Germany. Their platform uses virtualization technology, hypervisor, to integrate AutoSAR, AP, CP, and non-AutoSAR OS on a single multi-core ECUs, which achieve high levels of isolation between different virtual machine partitions. You can have a performance partition with complex performance cores for high performance subject to low levels of safety certification, and safety partition on the right with a simple safety core subject to high level of safety certification, and security partition with ARM trust zone Intel software guard extensions for secure boot, crypto operations, and so on. So relying on virtual machines can achieve high levels of isolation among different subsystems. So NVIDIA provides not just hardware, they also have a software framework called the Nvidia Drive. So the underlying hardware is their Xavier Pegasus GPUs, and then they provide operating system and networks, drive networks. The networks here means deep neural networks. They have a lane net, a drive net, map net, and so on. Calibration, and they have planning, mapping, and perception libraries for easy application development. So if you rely on NVIDIA hardware for autonomous driving, then you should use this framework, but it's specific to NVIDIA hardware. So DriveOS is a foundational framework consisting of real-time operating system, hypervisor, CUDA libraries, TensorRT, which is a TensorFlow library, and other modules. DriveWorks SDK provides a comprehensive library of modules. DriveAV provides perception, mapping, and planning modules. And DriveIX provides cabin interior sensing. For example, monitoring the driver. Baidu Apollo is an open source, hardware neutral AD platform from China. So it's initially based on ROS, but later they replaced the ROS with their own components. With the operating system is Linux kernel with real-time patch, and CyberRT is the lightweight, high-performance communication middleware. Here, this part. And all the usual modules are there: perception, prediction, planning, control, and so on. So it's fully open source. It's one of the two well-known open source platforms. The other one is AutoWare. It's an open source platform from Japan. So there are two versions. One is based on ROS 1, one is based on ROS 2. So as I said, the main problem with ROS is that it's difficult or impossible to perform high levels of safety certification with ROS. So that's why Apollo replaced ROS with their own system. But AutoWare still relies on ROS. So we have a few minutes, so we can, I think we can finish the ethical issues today. So there are two introductory videos, which, let me see, should I play it? Let me see how long it is. So I use the Opera browser, which has difficulties with Google Ads. with YouTube ads. It has to wait for the entire ad to finish. So let's play one video just for 3 minutes.
This is a thought experiment. Let's say at some point in the not-so-distant future, you're barreling down the highway in your self-driving car, and you find yourself boxed in on all sides by other cars. Suddenly, a large, heavy object falls off the truck in front of you. Your car can't stop in time to avoid the collision, so it needs to make a decision. Go straight and hit the object, swerve left into an SUV, or swerve right into a motorcycle. Should it prioritize your safety by hitting the motorcycle, minimize danger to others by not swerving, even if it means hitting the large object and sacrificing your life, or take the middle ground by hitting the SUV, which has a high passenger safety rating? So what should the self-driving car do? If we were driving that boxed-in car in manual mode, whichever way we'd react would be understood as just that, a reaction, not a deliberate decision. It would be an instinctual, panicked move with no forethought or malice. But if a programmer were to instruct the car to make the same move, given conditions it may sense in the future, well, that looks more like premeditated homicide. Now, to be fair, self-driving cars are predicted to dramatically reduce traffic accidents and fatalities by removing human error from the driving equation. Plus, there may be all sorts of other benefits: eased road congestion, decreased harmful emissions, and minimized unproductive and stressful driving time. But accidents can and will still happen, and when they do, their outcomes may be determined months or years in advance by programmers or policymakers. And they'll have some difficult decisions to make. It's tempting to offer up general decision-making principles like minimize harm, but even that quickly leads to morally murky decisions. For example, let's say we have the same initial setup, but now there's a motorcyclist wearing a helmet to your left and another one without a helmet to your right. Which one should your robot car crash into? If you say the biker with the helmet because she's more likely to survive, then aren't you penalizing the responsible motorist? If instead you say the biker without the helmet because he's acting irresponsibly, then you've gone way beyond the initial design principle about minimizing harm, and the robot car is now meting out street justice. The ethical considerations get more complicated here. In both of our scenarios, the underlying design is functioning as a targeting algorithm of sorts. In other words, it's systematically favoring or discriminating against a certain type of object to crash into. And the owners of the target vehicles will suffer the negative consequences of this algorithm through no fault of their own. Our new technologies are opening up many other novel ethical dilemmas. For instance, if you had to choose between a car that would always save as many lives as possible in an accident, or one that would save you at any cost, which would you buy? What happens if the cars start analyzing and factoring in the passengers of the cars and the particulars of their lives? Could it be the case that a random decision is still better than a predetermined one designed to minimize harm? And who should be making all of these decisions anyhow? Programmers? Companies? Governments? Reality may not play out exactly like our thought experiments, but that's not the point. They're designed to isolate and stress test our intuitions on ethics, just like science experiments do for the physical world. Spotting these moral hairpin turns now will help us maneuver the unfamiliar road of technology ethics and allow us to cruise confidently and conscientiously into our brave new future.
Okay, so the other one you can watch at home. So here's the classic trolley problem. So there's a runaway trolley barreling down the railway tracks. Ahead on the tracks, there are 5 people tied up and unable to move. The trolley is headed straight for them. So the trolley is going this way. So you are standing some distance off in the train yard next to a lever. If you pull this lever, the trolley will switch to a different set of tracks. However, if you notice that there's one person on the side track, you have two options. Do nothing and allow the trolley to kill the 5 people on the main track, or pull the lever, divert the trolley onto the side track while it will kill one person. So what's the right thing to do? So there are many variants of the trolley problem proposed initially by philosophers. The fat man, that is, you are on a bridge under which it'll pass, and you can stop it by pushing a fat man next to you. So your only way to stop the trolley to push him over the bridge and onto the track. So the fat man is the villain who put these 5 people in peril. The loop, trolley is hurtling down a track towards 5 people. You can divert it onto a secondary track, which later rejoins the main track. So that's the diversion of the track. So there's a fat man on the side track. So if you divert it, then the fat man will stop the 5 other people. And the main yard, so you can collide another trolley into it, but if you do, both will be derailed and will go down a hill and into a yard where a man is sleeping on a hammock. And he will be killed. So there are many variants of the problem. So let's put a little math into it. You are in a situation where if you kill a pedestrian with probability 1, but it's not your fault, or you kill a different pedestrian with probability P and it is your fault, what's your threshold value for making the choice? So if you're driving, say on the highway, and there's a jaywalker on the highway. So if you hit him and you kill him, it's not your fault. But you may choose to divert the vehicle on the side and hit someone on the sidewalk. And then it is your fault. But the probability of killing this person on the sidewalk is very small. But if you go straight and kill the jaywalker, then it's very certain that you will kill him. So what's the proper choice? Obviously, it depends on the threshold, right? So how high do you set the threshold? That's a very tricky ethical question. If the probability for hitting the pedestrian on the sidewalk is 0.001%, then you should divert the vehicle. But if it's 50%, yeah, you may think twice. So MIT provided a large-scale online survey in 2016. It's called the Moral Machine. So I think this is still online. Yeah, it provides a bunch of different scenarios. So here's a scenario where if you go straight, you kill the pedestrians. If you go to turn this way, you kill yourself by hitting the barrier. And you may have, going straight, killing yourself, or going on the side and killing the dogs and the pedestrians. And more dogs. And so there are many scenarios. You can even design it yourself. Yeah, here are 2 passengers killing 2 passengers or 5 pedestrians. So accident scenarios are generated with 9 factors: sparing humans versus pets, staying on course versus swerving, sparing passengers versus pedestrians, sparing more lives versus fewer lives, and so on. So it generated 40 million decisions in 10 languages from millions of people in 233 countries. So it has the survey result shows that the decision based on gender, fitness, social status, lawful, unlawful, age, number of characters, and also preference in terms of for example, for the attribute age, probability of sparing young characters is 0.49 with standard deviation, standard error of 0.008, greater than the probability of sparing older characters for the age. Yeah. And there are also cultural clusters divided into Western, that is Europe and North America, and Eastern, that's Islamic and Asian cultures, and Southern, that's Central and South America, as well as France and former French colonies. And they show different moral compasses. So for the Eastern cluster, the preference to spare younger characters rather than older characters is much less pronounced for Eastern culture. So I guess the Asian culture has more regard for the elderly. And also based on social status. So this figure shows the 3 clusters with different preferences. So AI ethical issues, is it worth the time? So many argue that ethical issues are just a distraction from the real problems of AV safety and security. So none of the AV accidents in the recent years involved any ethical decisions similar to the trolley problem. So they are due to failures in sensors or perception algorithms. So Sebastian Thrun, former head of Google's SDC project, who led the development of Stanley, winner of the DARPA Grand Challenge in 2005. He said that it's a great thing for philosophers to discuss these kind of problems. They can get tenure at their universities, but it's not of practical relevance, and so on, so on. So basically, he says that AD will be much safer and save so many lives that these kind of hypothetical scenarios are not a real issue. Whatever the outcome is, the mental energy that philosophers have spent on discussing is completely out of proportion to the benefit of others on one problem. So I will leave it at that. So indeed, right now, I think it doesn't seem to be a problem, mainly because these kind of dilemmas are extremely unlikely in real life. At least no AV has ever encountered this kind of dilemma up to now. So it's absolutely necessary to test AVs on public roads for technology development. Well, it is necessary, but is it ethical? So in the United States, the laws are different in each state. Some states allow have more liberal rules regarding AV testing. Nevada, California, Texas, Arizona. Others are more strict. So I think AV testing is on the road is okay if the human operator can be alert and responsible. So if you notice the common points among the 4 states, Nevada, California, Texas, Arizona, they all have dry, sunny weather, and that's important for AVs. If you are in Michigan or in Umia with all the snow, then it's pretty much impossible. So I think this little video clip is very helpful for understanding the moral machine experiment. So let's watch it.
Who would you save? The pedestrian in the road or the drivers in the car? It's not easy, and yet that's the kind of decision which millions of autonomous cars would have to make in the near future. We program the machine, but who do we tell it to save? That is the setup of the moral machine experiment.
There are so many moral decisions that we usually make during the day we don't realize. In driverless cars, these decisions will have to be implemented ahead of time. The goal was to open this discussion to the public.
Some decisions might seem simple. Should the car save a family of 4 or a cat? But what about a homeless person and their dog instead of a businessman? Or how about 2 athletes and an old woman instead of 2 school children?
The problem was that there were so many combinations, so many possible accidents, that it seemed impossible to investigate them all using classic social science methods.
Not only that, but how do people's culture and background affect the decisions that they make?
The only option we had really was to turn it into a viral website. Of course, it's easier said than done, right?
But that is exactly what the team managed to do. They turned these situations into an online task that people across the globe wanted to share and take part in. They gathered almost 40 million moral decisions taken from millions of online participants across 233 countries and territories from all around the world. The results are intriguing. First, there are 3 fundamental principles which hold true across the world.
The main results of the paper for me are first the big 3 in people's preferences, which is save human, save the greater number, save the kids. And the second most interesting finding was the clusters, the clusters of countries with different moral profiles.
The first cluster included many Western countries. The second cluster had many Eastern countries. And the third cluster had countries from Latin America and also from former French colonies.
The cultural difference we find are sometimes hard to describe because they're multidimensional, but some of them are very striking, like the fact that Eastern countries do not have such a strong preference for saving young lives. Eastern countries seem to be more respectful of older people, which I thought was a very interesting finding.
And it wasn't just age. One cluster showed an unexpectedly strong preference for saving women over men.
I was also struck by the fact that French and the French subcluster was so interested in saving women. That was, I'm still not quite sure what's going on here.
Another surprising finding concerned people's social status.
On one side, we put male and female executives, and other side, we put a homeless person. The higher the economic inequality in a country, the more people were willing to spare the executives at the cost of the homeless people.
This work provides new insight into how morals change across cultures, and the team see particular relevance to the field of artificial intelligence and autonomous vehicles.
In the grand scheme of it, I think these results are going to be very important to align artificial intelligence to human values. We sometimes change our mind. Other people next to us don't think the same thing we do. Other countries don't think the same things we do. So aligning AI and human moral value is only possible if we do understand these differences, and that's what we try to do. I so much hope that we can converge, that we avoid a future where you have to learn about the new ethical setting of your car every time you cross a border.
Okay, so we finished most of the introduction part. We have one last part on V2X communication, and then we'll go into the safety certification in next class. Any questions?
Yeah, I have a question regarding Lidar. So, as I could read it there, that Lidar is independent of lighting conditions, right?
Yes.
If you see here, so we have the device has sent one light signal and it received it. So how sunlight is impacting this, or it doesn't?
Sunlight does not impact the laser because it's not a visible light spectrum. If you notice the spectrum, the visible lights are in here, whereas Lidar is somewhere different. So they do not interfere at all.
So it is a laser then?
Yeah, it is a laser. Lidar is laser.
Okay. And one more question would be that when Lidar has sent the laser beam, how does it recognize that what is returned? So how does it correlate that? It doesn't.
All it returns is a bunch of points, a point cloud. So every laser beam hits the object and you get back a point. The point has no color, no other information, no pixel. It's just a single point that something is there. And then you get millions of points from a LiDAR scan. And then you need to process the points with either conventional algorithms or deep learning to learn about the objects, to recognize maybe that looks like a person's shape, looks like a car's shape. So yeah.
Object detection, object classification algorithm is the next step, right?
Yes.
Okay, thank you.
And the information you get back is much less detailed than the camera picture information. For example, you cannot really recognize the specific person's face. Only camera can do that. You can only see a person's rough shape. Yeah.
But the edges of the object can be recognized, right? Somehow.
Edge
of the object, like so this scene has the whole structure. The edge of this shape is somehow visible on the picture below on 3D point cloud.
So do you mean AGE edge?
Yeah, EDGE.
Edge.
Yeah, sorry.
Yes. Edge. So the most common framework is the point cloud library, pointcloud.org, for processing the LiDAR point clouds. So they have filters and KD tree and so on. So that's the conventional computer vision algorithm for point clouds. And also deep learning for point clouds is relatively recent. Maybe the PointNet was developed was the pioneering work in 2016 that applied deep learning on point clouds.
Okay.
Yeah. Okay, any other questions? Okay, so let's finish. Again, I exceeded for 15 minutes. Sorry about that. Let's see you on Wednesday. Okay, goodbye.
Thank you.